So in this lecture, we will discuss about the thermodynamic properties and relationships. Uh, so we have different properties which we use in normal calculations in thermodynamics, which are pressure, volume, temperature, density, or specific volume. A specific volume is a reciprocal of density, mass, internal energy, enthalpy, entropy, specific heat at constant pressure, specific heat at constant volume. We have a couple of other functions called Gibbs function and Helmholtz function. These are the properties generally we come across in any thermodynamic process, of which the properties like mass, volume, temperature, pressure. These four properties can experimentally be measured using some measuring devices. Like mass can be measured by weighing balance or something like that. Volume can be measured by knowing about the volume of the container, uh, if it's a gas or otherwise the volume occupied by the liquid or uh, solid material can also be calculated by different modes. Temperature can also be measured by proper thermometer. Pressure can be measured by pressure measuring devices like a manometer or pressure transducers or maybe by pressure gauges. So this anyhow, with the required accuracy, we can use different devices, but these four properties can directly be measured experimentally. Other properties cannot be measured directly. Of course, the density can be calculated by mass by volume, or the specific volume can be calculated by volume by mass. So, other than these 4 plus 1, 5 properties, other properties like internal energy, enthalpy, entropy, specific heat at constant pressure, specific heat at constant volume, Gibbs function, Helmholtz function, etc., cannot be measured experimentally. So it is necessary to form relations among different properties so that the unknown properties or the properties which cannot be measured experimentally can be calculated using the thermodynamic relations. For example, in a property, if we which involves a property relation which involves four properties, of which three can be experimentally measured. The fourth one can be calculated using the property relation. This is the essence of it. Now, why do we need the value, numerical value of different properties? The value of the different properties are very much essential in design of the engineering systems, engineering or other scientific experimental or research systems, etc. So the knowledge about the numerical value, exact numerical value of different properties or changes of different properties are very much essential. For example, suppose we have a pipeline through which a gas or a liquid flows, then the volume flow rate is required, is to be known, or the density of the material like a gas or the liquid is to be known for us to design or size the different parts of it, like the diameter of the pipeline is decided by the volume flow rate and the maximum velocity at which it can be passed through that. So based on this, we need to design the pipeline. Similarly, if you want to design an IC engine cylinder, we should know, say, the cylinder wall may have a limiting value for the pressure at a particular temperature, etc. So we should know what is the density of the gas at particular temperatures, how it varies, and things like that. So the knowledge about different properties are very much important in design of engines, turbines, structures, pipelines, refrigeration systems, and many other cryogenic systems, space vehicles. So for everything, we should have an idea. Not idea, we should know exactly the numerical value of different properties. So some of the properties can be calculated, measured experimentally. Other can be obtained by using proper properties relationships among these four properties and other properties. Now, uh, the properties relations can be of two categories. We can form relations among properties, uh, different properties between two different phases. Suppose when a process takes place and the substance in the which takes place in the process changes its phase, typically melting process or vaporization process. During these, the phase change takes place. It need not always be like melting or uh, like vaporization, etc. It can also be, say, suppose the crystal structure of uh, metal changes from alpha to delta or something like that. So there also we have phase change takes place. It need not always be from solid to liquid or liquid to vapor like that. It can also be other way of phase transition. So during these, the property relations have to be formed. Uh, but other types of relations are like when a thermodynamic process takes place and there is no change in the phase. Like a gas is heated inside a cylinder, it remains as a gas itself. Still, there will be property changes like pressure, volume, temperature, entropy, enthalpy, etc. All these properties can change during a process in which there is no phase change. So the property relations, some of the properties relations can be across phase change, or some other property relations are derived when the change takes place without a phase change, or the thermodynamic process takes place in a single homogeneous phase. So now if you analyze the different properties relations, we can see that some of the properties are in the will come under the first category and some property relations come under the second category. So we will see the important properties relations in each the cases. Now, the properties relations. So, the first category is the relations uh, for differences in the properties between two different phases, like during melting or vaporization, etc. Uh, uh, these phase change are of different can be classified in different ways. So the classification of the phase changes are based on something like something called the Ehrenfest classification of the phase transitions. So the classifications and the Ehrenfest conditions for different types of phase change operations, uh, like first order phase change, second order phase change, or higher order phase change. So these types of classifications, so it is defined as follows. So this is exactly the definitions given as per our first classification. So let's assume that there are two phases, alpha and beta, in equilibrium at a given coexistence curve. Like at a particular temperature and pressure, ice melts. So melting of ice can be considered to be a phase change operation. It need not always be melting. As I said, it can be different ways. We will get more idea when we complete this discussion. So let's assume that alpha is a solid ice and beta is liquid water. So they are in equilibrium at a given pressure and temperature. So we can plot the variation for different properties which takes place during melting process. Now, according to Ehrenfest, the order of the phase transition can be defined as the order of the lowest derivative of the Gibbs enthalpy G, showing a discontinuity upon crossing the coexistence curve. which is called the order of the phase transition. So I'll try to explain that. For example, uh, the order of the phase transition is simply, so it is Gibbs function, the derivative of the Gibbs function with respect to some variable. Say here it is temperature and pressure. So uh, we can see that the derivative, the mth derivative of G. So dou mga, dou to the power of m of the Gibbs function alpha divided by dou t raised to m. The nth derivative of Gibbs function of the alpha component, maybe solid ice, with respect to temperature to the power of m at a constant pressure, which is also equal to mth derivative of g beta uh, divided by dou theta raised to m at a constant pressure. So the mth derivative will be equal. That means the Gibbs function of alpha and the Gibbs function beta will be the same across this temperature pressure. As long as they are independently, it is independently kept constant. But the similarly, we can also write the mth derivative of G alpha with respect to pressure to the power of m at a constant temperature is same as mth derivative of G beta with respect to pressure to the power of m at a constant temperature. For say m can be 1 or 2, 3 like that. It can go like that. So the order of this phase transition is defined in such a way that up to a particular value of n minus 1, this will be continuous. That is the equality sign holds good. But the next derivative, nth derivative. So dou raised to n g alpha divided by dou t raised to n at a constant pressure will not be equal to dou raised to n g beta divided by dou t raised to n constant pressure. So then the order of the derivative at which it becomes unequal or discontinuous is called the order of the phase transition. So same is the case with the dou raised to n g alpha divided by dou p raised to n, while temperature raised is kept constant, will become not equal to, or this function becomes discontinuous across the uh, phase transition point. So then it is called the transition, phase transition is of the order n. N minus 1 where that will be continuous and the nth derivative will be discontinuous. So that is what we mean by saying that the phase transition is of nth order. But in practice, only first order phase transition and the second order phase transition are of importance. And we will discuss only the first order phase transition. And second order, we can have maybe a very limited number of examples are available for the second order phase transition, but we will not discuss. We will discuss only this uh, in properties relations. So we will see this by an example. For example, let's see first order phase transition. So in first order phase transition, the Gibbs function at a constant temperature, I mean, which is a function of temperature and pressure, will be continuous across a phase transition. For example, this is melting. Melting, the value of the Gibbs function will be continuous across this one. But uh, the first derivative, that is, we can see that from the Maxwell's relation, dou g by dou t at a constant pressure is equal to minus s. So this relation, we will see this relation later. Anyhow, the first derivative dou g by dou t at a constant pressure is equal to minus s, or S is equal to minus of dou G by dou T at a constant pressure, and volume is equal to dou G by dou P at a constant temperature. So we can see that across a melting process, the entropy value of the entropy, if you proceed from the left and that from the right, we will get two different values. So at the beginning of the melting process, the entropy has some value. At the end of uh, this melting process, when the complete ice has been melted to liquid water, it will have another value for entropy. So even at a constant pressure and temperature, the entropy value at two ends of this process will be different. So at a constant pressure temperature, it has a discontinuity in the value of entropy. And similarly, it has a discontinuity in value of the volume, because the volume of the ice decreases during melting process. Uh, for water only, this phenomenon is there. So we can see that the first order derivative of the Gibbs function, it is discontinuous. So we can see that uh, this is a first order phase transition. Melting or vaporization process is a first order phase transition because the first derivative of the Gibbs function with respect to temperature uh, is discontinuous. Similarly, first derivative of Gibbs function with respect to pressure at constant temperature is also, that is nothing but volume, which is discontinuous. So there is a step you can see. Similarly, uh, so at a constant temperature, we can see the entropy change is there. It is not continuous function. So if you find the limit of the function from the left and from the right, they will be unequal. So this mathematically we studied this in class 11 or class 12, etc. Now let's see another case in which it is a second order phase transition. So let's see the case of a second order phase transition. Uh, so I think before going to this, we should also see a property relation. Some of the property relations we should be familiar with at this point. Uh, yeah. Uh, Before going to that relation, uh, we have the combined first and second law. So we have four equations. Actually, from these four equations, we derived the Maxwell's relations. But before going to Maxwell's relations, we will see this relation. Say, du is equal to TdS minus PdV. We know that heat is equal to Q is equal to dQ is equal to du plus PdV. In a reversible process, we can write dq is equal to tds. So tds is equal to du plus pdv. This relation we know. So we can write this du is equal to tds minus pdv. So from this relation, from this combined first and second law relation, we can form an equation. Say dou u by dou s as volume is held constant. What is dou u by dou s as volume is held constant? When volume is held constant, dv becomes 0. So the second term on the right side of the equal sign vanishes. So dou u by dou s at a constant volume is equal to temperature. So this relation is made use of there. Similarly, we can take the other combination dou u by dou v at a constant entropy. Dou u by dou v at a constant entropy. So at a constant entropy, TDS will become 0. Isentropic process, TDS becomes 0. So dou u by dou v at a constant entropy equal to minus P. So u by dou v at a constant entropy is equal to minus P. Similarly, we can form other relations as well. So dH is equal to TDS plus PdP. This holds good for any type of processes. So dou H by dou S at a constant pressure is equal to temperature. Dou H by dou S at a constant pressure equal to temperature. And similarly, dou H by dou P at a constant entropy is equal to specific volume. Dou H by dou P at constant entropy equal to specific volume. Here, in these relations, we have used the specific terms. like a specific energy, specific enthalpy, specific Helmholtz function, and a specific Gibbs function. So when we write the specific equations, temperature is an intensive property and pressure is also an intensive property, but volume becomes specific volume. Similarly, entropy becomes specific entropy, like that. So depending on whether it's a capital letter or small letter, here on entropy, internal energy, enthalpy, etc. also becomes correspondingly small letter specific terms. So now also from the other combinations like Helmholtz function, I think you remember the relation Helmholtz function. Here it is represented by A. Helmholtz function is equal to U minus Ts. U minus Ts. Similarly, Gibbs function is defined as H minus Ts. So, using the relations first and second laws, we can write dA is equal to minus SdT minus PdV. You can get this relation very well. We will also derive these relations when we derive the Maxwell's equations. Similarly, so from this dA is equal to minus SdT minus PdV relation, uh, taking the partial derivative of the Helmholtz function, dou A by dou V at a constant temperature is equal to minus P. Dou A by dou V at constant temperature is equal to minus P. And similarly, dou A by dou T at a constant specific volume. Dou A by dou T at constant specific volume is equal to minus S. Similarly, from the Gibbs function relation, dou G by dou P. Dou G by dou P at constant temperature is equal to specific volume, and dou G by dou T at a constant pressure. Dou G by dou T at constant pressure is equal to minus S. So these are the additional relations which we obtain from these four equations. These four equations, equation 1, 2, 3, 4, du is equal to dH is equal to d Helmholtz equal to, similarly d Gibbs equal to. These four relations are generally we use this to derive the Maxwell's relations, and in addition to Maxwell's relation, we can also get these property relations. This will also be made use of conveniently for getting other properties relations. So from this property relation, so dou U by dou S at constant volume equal to temperature, and dou U by dou V at constant entropy equal to minus pressure. These relations can be used here also in defining the phase transition. In second order phase transition, entropy is equal to, from the fourth equation we can write entropy is equal to minus dou G by dou T at constant pressure, and volume equal to dou G by dou P at constant temperature. And for first order phase transition, this becomes discontinuous. First order derivative itself becomes discontinuous. But for second order phase transition, we'll see an example of second order, but we can first have the Ehrenfest condition for this. So the Gibbs function during a second order phase transition will be continuous, and the first order derivative will also be continuous for second order phase transition. First order derivative means S is equal to dou G by S is equal to minus of dou G by dou T at a constant pressure. This will also be continuous. So entropy change will be continuous. The value of the entropy at any point at a constant pressure, at the point at a constant pressure will have the same value if you approach the limit from left or from the right. So that's what it is, the function is continuous. Similarly, the volume which is given by dou G by dou P at a constant temperature, this will also be continuous for the second order phase transitions. The first derivative of the Gibbs function will be continuous for the second order phase transition. It is only the second order derivative which are going to be discontinuous. So the discontinuities in the second order derivatives of the Gibbs function, temperature and pressure. This is if we have a two component system, n will be 2. So uh, G, temperature, pressure and components leads to discontinuities of the response function. That is, a second order derivatives will become discontinuous. So uh, we can see that again we can see we can obtain this relation. Specific heat is equal to T into dou S by dou T at constant pressure. We can see this relation. So but dou S by dou T, S is equal to minus of dou G by dou T. So S is equal to minus of dou G by dou T. So dou S by dou T will become dou by dou T of dou G by dou T minus dou G by dou T. So it becomes T into by with a negative sign into dou square G by dou T square at a constant pressure. So the specific heat, which is actually minus T into dou square G by dou T square at constant pressure, and uh, the isothermal compressibility, the isothermal compressibility, one second, uh, isothermal compressibility Kt or kappa T is equal to minus 1 by V into dou V by dou P at constant temperature. This again becomes minus 1 by V into dou by dou P, and volume is equal to dou G by dou P at constant temperature. From the previous slide we can see that volume is equal to dou G by dou P at constant temperature. So we can see that Kt, that is isothermal compressibility, uh, is equal to minus 1 by V dou square G by dou P square. And similarly, the thermal expansion coefficient alpha is given by change of volume per degree rise of temperature per original volume. This is a thermal expansion coefficient 1 by V dou V by dou T. 1 by V into dou by dou T of volume. Dou by dou T of volume is dou G by dou P, dou G by dou P. So this becomes 1 by V into dou square G by dou T dou V, dou P, sorry. So these three parameters, this becomes the second derivative of the Gibbs function. Second derivative of the Gibbs function, dou square G by dou T square, and Kt is something multiplied with the dou square G by dou P square, and alpha something multiplied with the dou square G by dou T dou P. So here in all these specific heat at constant pressure, the isothermal compressibility, and also the thermal expansion coefficient alpha, these are all having second order derivative of the Gibbs function uh, with the pressure or temperature or combination. So these things will become discontinuous. These derivative becomes discontinuous. The second order derivative becomes discontinuous in a second order phase transition. So in these relations, we can see that the value of Cp during the phase, that particular second order phase transition will be discontinuous. The specific heat value changes drastically during certain stage. So a second order phase transition, example for the second order phase transition can be say found in the superconductivity ranges, when the material is cooled and becomes uh, near the superconductivity region. uh, at that point, we can see that the specific heat, the conductivity, and many parameters change drastically. So, even though the entropy, the volume, etc., the first order derivatives are continuous, we can see that during second order derivatives, typically like a superconductivity range, the values Cp, Kt, and alpha, etc., they change drastically. So these changes normally we do not discuss in our course, but this can find application in cryogenic applications and superconductivity, etc. So phase transitions of the second order show a finite discontinuity in the specific heat Cp. An example is the transition to a superconducting state at zero magnetic. In the absence of any magnetic field, superconductivity state, the transition during that state is an example of second order phase transition. So here we had seen that we can make property relations across the same phase change, same phase processes, or a phase change of the first order or a phase change of the second order, like that. So now if you see, there are different properties. We'll skip this for the time being. Properties relationships, some are across phase transition and some property relations are valid in the same phase. So now we can see some of the properties relationships. First we will go to the Maxwell's relations. Maxwell's relations. So before going to Maxwell's relations, we can see the mathematical condition for continuity of a function at a state. Consider a variable. A variable means it's a thermodynamic property that is a continuous function of x and y. So generally, mathematically, we can say any function is a property if it satisfies these continuity relations. So if you are given any combination of the properties, etc., and if we can prove that it is a continuous function at some point, then it becomes a property, thermodynamic property. So let's assume that we have z is equal to a function of x and y. Z is a property, x and y are also properties. Z is going to be a function of x and y. Now, the derivative, the exact differential dz can be written as dou z by dou x at keeping y constant into dx plus dou z by dou yx into dy can be written like this. So, some of the partial derivatives multiplied with the corresponding changes. And let's take this dou z by dou x a constant y, say we can call this function m, and dou z by dou y constant x, let's call this n. So for the function to be continuous, so what will be the condition? Dou m by dou y, the next derivative, dou m by dou y, you just swap the independent variable, dou m by dou y x is equal to dou n by dou x y. That is, if the order of differentiation is changed, swapped, the function will be continuous or function will be equal. Then this is a condition for the continuity of the function. So in that way, if you take the next derivative, dou by dou y of dou z by dou x, because m is dou z by dou x, is equal to dou by dou x of dou z by dou y, like that. So in that case, dou m by dou y at a constant, while x is constant, is equal to dou by dou y of dou z by dou x. So this becomes dou square z by dou x dou y. Similarly, dou m by dou n by dou x, dou n by dou x at constant y will become dou square z divided by dou y dou x. So from these two relations, the order of the differentiation is swapped or changed. And if we can show that these two functions are equal, then these two derivatives are equal, then the function is continuous across that point. So the condition that dou square z by dou x dou y equal to dou square z by dou y dou x, then if this condition is satisfied, we can say that dou m by dou y at x equal to dou n by dou y, or it is a continuous function. It is a continuous function. For a continuous change of the function, uh, we can that is for single phase. We can make Maxwell's equations. So Maxwell's equations are derived from the uh, energy equations. Energy equations. So we know that du is equal to TdS minus PdV. Uh, I think there is no problem with this function uh, because we have, if you want, I can write this. We have dq is equal to du plus pdv. This is specific properties. 1 kilogram of a system or of a substance. This have only pdv work. No other work is there, and only internal energy change is there. This is stationary system. Or uh, for reversible process, dq is equal to TdS for reversible process. So we can write TdS is equal to du plus PdV, or du is equal to TdS minus PdV. Let's call this first equation. From this we can make the first Maxwell's relations. So let's call this equation 1. Similarly, dH is equal to d of u plus PV, which is equal to du plus P into dV plus V into dP. But du plus PdV, what is this? TdS. So this is equal to TdS plus VdP. So dH is equal to TdS plus VdP. Let's call this equation 2. Now we have Helmholtz function. See the spelling also. So here Helmholtz function is given in this presentation. It is given by A. So let's call this, represent this by A. So A is defined as u minus Ts. So specific Helmholtz function. So dA is equal to du minus Tds minus S dt. So TdS minus, sorry, see this du is equal to TdS minus PdV. So what is minus of this? Du minus TdS. So du minus TdS equal to minus PdV. You can see from this relation, equation 1, du minus TdS is equal to minus PdV. So this can be replaced with the, so dA is equal to minus PdV minus S dt. Let's have this as the third equation. We call this equation 3. Similarly, Gibbs function. Now, Gibbs function is defined as H is equal, sorry, Gibbs function is defined as uh, G is equal to H minus Ts. Again, specific terms, this is also small s. So dG is equal to dH minus TdS minus SdT. Now, from the second relation, dH minus TdS, what is this? dH minus TdS. dH minus TdS equal to plus VdP. So, sorry, this has to be G. So, dG is equal to VdP minus SdT. This is our fourth equation. So, we have four equations here. Now, these four equations, again, we go to the PPT. First equation is du is equal to TdS minus PdV. Second equation is dH is equal to TdS plus VdP. And Helmholtz function is written like this. So, dA is equal to minus STT minus PdV, third equation. And Gibbs function dG is equal to minus STT plus VdP. These four relations are there. Now, from these four relations and also considering the fact that properties are continuous functions in a single phase uh, process, I mean, say the changes which takes place the same uh, phase, I mean homogeneous phase, then the functions will be, the properties will be continuous, and for a continuous function dz can be written as m dx plus n dy such that dou m by dou y at a constant x, dou m by dou y at a constant x is equal to dou n by dou x at a constant y. We'll go to the presentation now. So, considering this also, dou m by dou y. So, if something can be written as m dx plus n dy, dou m by dou y. So, from the first relation, we can write dou t by dou v at a constant s. Dou t by dou v at a constant s is equal to dou p by dou s at a constant v. So, dou t by dou v at a constant s is equal to, there is a negative sign also. So, minus of dou p by dou s at a constant v. So, this is a first Maxwell's relation. Now, from the second equation, similarly, the second equation, so this is dH is equal to TdS plus VdP. From this relation, we can write dou t by dou p at a constant s is equal to dou v by dou s at a constant p. So, dou t by dou p at a constant s is equal to dou v by dou s at a constant pressure. This is the second Maxwell relation. Now, from the third equation, which is obtained from the definition of the Helmholtz function, dA is equal to minus SdT minus PdV. So, the third Maxwell's relation will become uh, minus of dou S by dou V at a constant temperature. So, minus of dou S by dou V at a constant temperature, which is written on the right side, uh, is equal to minus of dou P by dou T at a constant volume. So both the terms has minus sign, negative sign, so that they will get cancelled. So the third Maxwell's relation will have both the terms as positive. Dou p by dou t is equal to dou s by dou v. It should be written like this. Similarly, from the fourth relation, which is obtained from the definition of Gibbs function, dg is equal to minus SDT plus PdP. So from this relation we can see that uh, minus of dou V by dou T at a constant pressure is equal to negative dou S by dou P at constant temperature. Dou V by dou T at constant pressure is equal to minus of dou S by dou P at a constant temperature. These are the four Maxwell's relations which are applied in the thermodynamics. Maxwell's relation can also be obtained in electromagnetics and things like that. But here we define Maxwell's relations in thermodynamics. Uh, so this you might have studied in thermodynamics, but here we will also uh, uh, try to apply the relations, properties relations which we derive here for some simple engineering calculations. So the order and the left time and right time are maybe it's better to write like this only. Dou t by dou v. This is the first Maxwell's relation. This is second Maxwell's relation. Third one and fourth one. We can see that fourth equation is the reciprocal relation of the first equation. So dou v by dou t is equal to dou s by dou p. And dou v by dou t is equal to dou s by dou p. And the variable here, the dependent variable here will become the constant here. And the dependent variable on the right side, independent variable on the right side becomes the constant here. Not dependent variable, independent variable. So similarly, the second and the third equations are also reciprocals. So dou t by dou p, here it becomes dou p by dou t. And dou v by dou s, the third equation, it becomes dou s by dou v. And once we write like this, the constant becomes such as swap this. Here v is the variable in the denominator, so v is a constant here. And t will be constant on the right side. So you can easily remember also this relationship. These are the four Maxwell's relations. In addition to the Maxwell's relation, a number of other useful relations can also be derived as below, which we had seen some time back. From the first energy equation, du is equal to TdS minus PdV, dou u by dou s at constant P is temperature and dou u by dou v at constant S is minus P. Similarly, dou H by dou S at a constant pressure is temperature and dou H by dou P at a constant entropy becomes the volume, and dou A by dou V at constant temperature from this relation, third relation, dou A by dou V at constant temperature becomes minus P, and dou A by dou T at constant volume becomes minus S. So uh, uh, there may be some say confusion when we try to write these equations, but if you make this equation, this can be easily written. So if you have this equation from this relation, you can form Maxwell's relation as well as these extra property relations. These equations or relations will also be useful in derivation of other parameters. So in this uh, presentation, we had seen the phase transition, first order phase transition, second order phase transition, and also we had seen the thermodynamic processes taking place during the same phase, that is homogeneous phase. So we can have thermodynamic systems in homogeneous system, homogeneous phase or during phase transition, and phase transition itself can be of first order, second order, or maybe higher order, but we don't have any higher order systems as of now. So we discussed about only three systems: homogeneous processes or changes taking place during homogeneous systems, processes, and also during phase transition. So uh, then we derived the Maxwell's relation, which is property relations taking place during in the same phase. Now we have other relations like the Cauchy-Clapeyron equation, which is derived during phase transition. So the thermodynamic changes which takes place during phase transition, of the first order phase transition. Melting, vaporization, etc. are examples of first order phase transition. Uh, we may also have such property relations like Gibbs function, etc. During material science, metallurgy processes, etc., which is beyond our scope. So we'll wind up this session, this video. The next presentation will be on the derivation of Cauchy's-Clapeyron equation and the application of Cauchy's-Clapeyron equation.